Okay, so Calculus BC lesson 6.2. This is just half of it. This is half of 6.2. We're going to move beyond finding area between two curves. Today we're going to find volume, and actually today we're only doing one of these methods. We're going to find volume using the disk method. Next time, next class, we're actually going to review the disk method, and then we're going to learn the second method called the washer method. But here is what's happening. When you revolve, when you spin a region around a line, you will get a solid of revolution. Case in point, you can see this picture right here. We've got this blue region. It's bounded by f of x and the x-axis. And what if we rotate this region around the x-axis? You'd get the solid that you're seeing to the right. So we can take a region. So those of you involved and interested in engineering, you can see there's some really cool possible applications. You could create solids in this kind of a manner. Well, how would you calculate it? We're going to be talking exclusively today about the disk method. And here is why. If you go back to rotating that blue region, imagine that you're just rotating one rectangle, because that's really what you were doing with area. When you were setting up an integral, we'd set up something called a Riemann sum. You might have had an LRAM, you might have had an RRAM, an MRAM. At the end of the day, though, we would work with an infinite number of rectangles. And that could be used to determine area. But look what's happening here. What if we took one single rectangle, just one, and we rotated that, we revolved that around the x-axis? Guess what kind of a shape you would get? You would get a disk. You would get a disk. And that's really what we're seeing right here. If you took that yellow rectangle, if you said, hey, I'm going to spin that yellow rectangle around the x-axis, you would create a disk. Say, oh, okay. This is why we're calling this the disk method. The disk method, essentially, we're still going to set up an infinite number of rectangles, but we're going to rotate them around an axis, and you will get an infinite number of disks. Now, here's what we need to know from geometry. This is really a circular prism, and the volume of this cylinder here. So as you're looking at this, you could say, well, anytime you find the volume of a prism, you take the area of the base. Well, guess what that base is? It's a circle, right? You can see that right there. It's pi r squared. And what's your r? Well, you can see your r was the height of the rectangle. That was your function value. Now you could say, well, I wonder what the thickness is, the distance between those circles. Well, that's your height. That's going to be delta x. So that real quickly is what we have for the disk method. The disk method is always going to have this kind of a format. You're going to have a region bounded by a line. For right now, it looks like we're focusing on an axis. We're going to see later on we can move beyond that. But you could say, well, if you're on the x-axis, you got that region. You could say, well, there's f of x squared. That's your pi r squared. Dx is going to be the thickness of that disk. It's the distance between them. The pi f of x squared dx, that's the volume of one little disk. Imagine that this limit right here is saying build an infinite number of them. So we're going to slice this up into an infinite number of thin rectangles where when we rotate them around, we're going to get these little disks to add up, and that's how we're going to find volume. Now, of course, here is the corollary. You could say, well, wait a minute. Last time in 6.1, we saw that we could find area really going in terms of functions of y. And this is exactly what we're going to see here. Your curve could be bound not by the x-axis, but by the y-axis. And you could say, well, hey, I could rotate around the y-axis. If you look at it, you can see a rectangle now is not going to have a top minus bottom connotation. It's going to be a right minus left. So it's very much in line with what we did in 6.1. So all the same, this rectangle right here would be a function of y. G of y would be your radius. So it's still pi r squared times the distance between it. It's just that everything is with respect to y. So let's get into this. Our notes now will just be the rest of this page. Just the rest of this page. And we'll do a number of problems to get you some practice. But look, for the disk method, draw a rectangle as you're asked to find volume. Draw one rectangle, but make sure it's perpendicular to the rotated axis. That's super, super, super important. And if you remember that, it's going to help you know with respect to which variable you're working in. And that's the key. Because sometimes kids will go, should I make this a dx problem? Should I make it a dy problem? If you set up a rectangle perpendicular to your rotated axis, especially when things get more complicated, that will unlock the problem for you. Okay? So watch what the directions are. Sketch. It doesn't have to be a super accurate picture. Just make a rough sketch and draw one rectangle, and then that can really help you out. So listen, let's do this together right now for example 1. So sketch the region, find the volume by generating it by revolving around the given axis. So immediately we know that we're going to rotate around the x-axis. So listen, I'm going to make a quick sketch, and we could say, wow, we've got y equals 1 over x. Such a famous curve, guys. Such a very famous curve. It's this right here, right? And of course, kids will say, now wait a minute, isn't it also in the third quadrant? Yes, yes it is. But I think you're going to see real quickly, this is one of those things that, guys, I strongly would recommend that you, just memorize that shape, the 1 over x shape. It's definitely an important one. You can see, hopefully you've done that in AMA and in Algebra 2, but you can see it looks like that, right? So we've got that curve, but we're only going to go between x equals 1, x equals 3, y equals 0 is the x-axis. So please notice what's happening. We're saying this right here, here's that x-axis, here's y equals 0. Guys, look at this. This is your enclosed region. It's this thing, right? And they're saying, please spin that around, rotate that around the x-axis. Now, at this point, I think kids can get a little bit uncomfortable. They'll say, do I have to draw a super detailed picture as to what that volume would look like? Thank goodness no. It's worthwhile, and I think if you've got some interest in engineering, maybe you want to do that, and maybe you want to say, yeah, what would that look like? We can talk about that a little bit. For right now, though, please go to the top of your notes and say, you know what? Disk method, this is what we're dealing with today. Make sure your rectangle is perpendicular to the rotated axis. Draw one rectangle, just one. One's good enough. And that rectangle right there is going to always be your radius. It's going to be your radius. So remember what we just saw a little bit earlier. Oops, pardon me. That's little bit crazy right there. Let's see if I can grab the slider. You can see really at the top of the page right here, this is where we're going. This is what we're trying to move towards. So I'm going to say I need to get the volume. That volume is going to be the integral. And I'm going to go from x equals 1 to x equals 3. I'm going to have a pi here, but now I need my radius. The radius is always going to be the length of the rectangle. And I know this is going to look odd when I write it now, but it's going to make hard problems easier. Always, always, always do top minus bottom or right minus left. What do you think we have here? Top minus bottom for the rectangle's length or right minus left? Well, top, look at this. Here's your top. Here's your bottom, right? So we're going to say it's 1 over x minus 0, and it's squared. It's radius squared. What am I saying? You're always going to have a top minus bottom. Most of the time, the problems that we're used to working with, guys, are going to look something like this. So it's pi radius squared dx. Here's the beautiful thing. Now it becomes a routine integral problem, right? And you'd say, what do you mean by that? I mean, right now, I could give this to students who are in chapter 4 and say, hey, if you've learned the fundamental theorem of calculus, you can do this problem. You might not realize you're finding volume, but you can do this problem. Yes? Don't you have to multiply the height by delta x? Well, the dx is hidden right in here, and because we have an infinite number of them, those heights are so super tiny, the dx is getting multiplied right here. Yeah, so we are doing pi r squared, and this would be the height, the distance between. So it all gets absorbed in there. But now we just do the fundamental theorem. You see, here's what we'll do. We'll say here's 1 to 3. By the way, if you want to pull pi out, so many kids do that. So many kids do that. They'll say, well, this is 1 over x squared dx. And then they say, well, how do I do this? Well, plain and simply, here, let me scroll this over. My computer's being a little uncooperative here. Here's your x to the negative 2. I am so sorry. This is x to the negative 2. How do we take an antiderivative? What do we have to do here? Yeah, add 1 to our power. Add 1 to negative 2, you're at negative 1. Divide by a negative, and then you've got this, and then you finish off the fundamental theorem. And kids might go, wait, Mr. Dobner, I'm really bugged by this. Your answer is going to be negative. You said that the answers in 6.1 and 6.2 are always positive. Yes, they are. And kids will say, oh, we're in trouble. Hold on. Let's just see here. Yeah, I know we've got negative pi out here, and then you could say x to the negative 1, well, that's 1 over x. And you'd say, well, hey, let's work this out. I've got negative pi. Now I go 1/3 minus, well, plug in your 1, you just get a 1. Oh my gosh, we are okay, aren't we? 1/3 minus 1 is negative 2/3. Multiply it together, you will get a positive 2 pi over 3. If you ever get a disk method where you get a negative answer, something went wrong. Just like the problems in 6.1, the area between two curves. If you ever get a negative answer there, go back and look at it. Something went wrong. Every one of these is going to be positive because we're going to go back to traditional area, traditional volume. Okay? We doing okay? So you just found that, wow, I could get the volume between those curves. Or no, the volume rotating that 1 over x around the x-axis from 1 to 3. So, wow. And sometimes kids will say, well, wow, what would that look like? Well, you could go ahead and you could begin to sketch some of that out. But again, for the sake of the video, I'm just going to keep going. Look at this, y-axis. Whoa. Y-axis. Automatically, something's different. Kids will go, wait a minute. I'm going to have this, y equals x squared. Oh, you know what? I'm so sorry. I meant to put in the line x greater than or equal to 0 here. I meant to tell you that. Without that, it would be a little bit of a confusing problem. Some of you might have worked ahead already. You could say, well, yeah, look, we've got a parabola right here. We've got y equals 2, and we've got that right there. And you could say you're going to rotate that around the y-axis. But you know what? Your region is only in the first quadrant. Sorry, I forgot to put that in there, right? X greater than or equal to 0. So you might see a little inequality in there sometimes. And kids will look at that and they'll go, oh, top minus bottom. Well, hold on a second. You're going to notice already, this is kind of looking weird. Please go back to the top. Rectangles are perpendicular to the rotated axis. We're trying to find volume, but if I were to go perpendicular to the y-axis, I'd get a rectangle that looks like that. Do you see what we're talking about? Are those the rectangles that we were working with in Chapter 5? Did we set up LRAMs and RRAMs and so forth that looked something like that? Not from the y-axis, right? This is kind of weird, right? So we're going to have to go with functions of y. You're going to have to take your equation, y equals x squared, solve for x, and you could say, well, let's see, I'd have x is plus or minus the square root of y, and you know what? X can only be positive, so x is only going to equal the positive square root of y. We doing okay with that? All right, so from here, I want you to see that this is really like the bottom of page 1's notes. This is this stuff right here. In other words, we need to have, we need to have our functions with respect to y, and we're integrating with respect to y. My integral has y boundaries. I still have pi r squared, and then we'll have a differential. So let's see if we could real quickly come back down here and fix this up. So I'm going to say my volume is the integral. I could still have a pi, but now I need a radius squared. And this time I'm not going to do top minus bottom. This time I'm going to do right minus left. Right minus left. What's the right boundary of my rectangle? Radical y. And what's my left boundary? X equals 0. We need x equals equations for these, not y equals, right? You'd say, oh, I'm going to square that. And then I'm going to integrate with respect to y. And I want all such rectangles going in this direction from y equals 0 at the origin up to y equals 2 up on top. Is this making sense? It's a little bit different. A little bit different. But what are we seeing? We're finding this volume, and some of you already can see, like if you rotated that around, it would kind of be like a gumdrop shape. But wow, let's clean this up. All of a sudden, kids will say, well, wait a minute, Mr. Dobner, if you're going to square a square root, won't the square root just go away? Yep. You could pull pi out. So, okay, you doing okay? Oh, where'd we get that 2 up on top? So, see, you're looking for all these rectangles Where's the top of the boundary? You're looking at y boundaries here. You're going to go from y equals 0 up to y equals 2.
The whole thing is in terms of y?
Yes, the whole thing is in terms of y when you're going to rotate around the y-axis, or for that matter, any vertical line. You're going to see what we're talking about. So now what? Now, even if you had no idea that we were finding volume, this becomes a Chapter 5 problem. And you can see the most important sounding theorem that you'd ever have is the fundamental theorem of calculus. So we're going to say, well, how do I do this integral? Got to do an antiderivative, right? Antiderivative of y is what? Y squared over 2. Plug in your upper bound, plug in your lower bound. And you could say, well, I'm going to keep a pi over 2 out in front. And then what? You go 2 squared minus 0 squared. And 2 squared is just a 4. And of course, 0 squared is just that. So what's pi over 2 times 4? Just 2 pi. That's the volume. That's the volume. If you rotated that thing around, you would get more or less a gumdrop kind of a shape, right? I think sometimes, and like I was saying, you don't have to, envision what's happening, revolving it around. Okay. We doing okay? All right, last one. Oops. Wow, my computer is misbehaving again. Let's see here. Let's come back over here. Wow. Wow, wow, wow. Automatically, I think you can see something's different. And this is probably worth saying. You can revolve around horizontal or vertical lines. By the way, the College Board rarely will ask you to revolve around an x-axis or a y-axis. It's far more likely, it's almost a given, that instead you're going to revolve around a line like y equals 4 or x equals 2 or something like that. So we need to know how to do that. So look, at first glance, you're probably going to say that the problem doesn't look so bad. Look at this. You can say, hey, we've got this right here. We've got our graph. Y equals x squared, one of the most famous graphs that you're ever going to see. It's a parabola that opens up. Y equals 4, you could say horizontal line. Look at that. And then you go, oh, you're enclosing a region. Oh my gosh, it's this thing. Oh, pardon me. It's this shape right here. But look, we're not going to rotate that around the x-axis, the y-axis. We're going to revolve that around the line y equals 4. Holy cow. All of a sudden, kids will go, oh, are you kidding me? You're going to spin that yellow region around y equals 4? We're going to get a three-dimensional solid? I'm trying to find the volume of that? Holy cow. Well, first off, at the top of the page, they'll say make a rectangle perpendicular to the axis or the line that you're going to revolve around. Make a rectangle perpendicular to that line in the region. And that's what I've just done. You see that? Yes. No, yeah, Matthew, you're so right. I mean, look, some kids are going to say, can I draw one right here? You bet you could. Kids will say, can I go right down the y-axis? You bet you could. You're free. The only reason why I'm doing this is right now I've got to figure out, I've got to think, hey, is this problem with respect to x or is it with respect to y? Right? And you look at this, look at that rectangle to find its length, to find out how big that rectangle is. Do we do top minus bottom or do we do right minus left? Yes, top minus bottom. And that's why I said in 6.1, that type of thinking is so critical and essential to be successful in 6.1 and really for the rest of chapter 6. Setting it up, you want to think this way. And you're saying, okay, so I'm stacking this up. These are the Riemann sums that we would have done in chapter 5. This would look like an LRAM problem or an RRAM, whatever you'd set up. In other words, it's with respect to x. It's not looking like we did at the top of the screen there where you go, ooh, we're not used to stacking them going, upwards like that. That's where we've got to change everything with respect to y. You got to solve your equations for x equals to get something with y in it. But right now you'd say, well, wow, you know what? I'm going to have a pi. I need a radius squared. Oh, wow, let's think about this. Top, what's the top that we have in this? It's y equals 4 minus, because it's top minus bottom. What's the bottom?
0.
And then you're squaring that whole thing. You see what we just did? Top minus bottom is for this radius. This was our top. This was our bottom. We doing okay? Now, we still have to talk about bounds. And kids will go, bounds? Well, yeah, we've got numbers on this integral. And you'd say, well, wow, if this is y equals x squared, when does x squared equal 4? And kids will go, oh, I know. Square roots, and what would x equal?
2.
Plus or minus 2. See that? So you're saying build all these rectangles that you just drew one of or two of. Please do that from x equals -2 to x equals +2. And then what? The 4 minus x squared is the height of that rectangle. It's really the radius length. We're going to square it. We're going to do pi r squared. Dx is that little bit of thickness, the distance between it. That's the volume of one little baby disk. Do all those sums of disks from x equals -2 up to x equals +2. That is your volume. We doing okay? Now, listen, of course, right now, we could just say, oh, right, I'll stop the video right here and we'll say, just work this out with the fundamental theorem. And you can, but listen, instead, I just want you to notice that this function inside is an even function. Watch. You don't have to do what I'm about to show you. But what I'm saying is an even function means if you plugged in opposite x instead of x, you get the same thing as just plugging in an x after you simplify. Kids might say, help me out. What are you really saying? Look, if f of x is equal to 4 minus x squared, if I had that, then what I'm getting at is f of opposite x equals 4 minus, well, you'd have an opposite x, square it, and when you square that, it's like the negative goes away. You'd say, oh, that's the same thing. This is an even function. And even functions have a property, but I bet you some of you would have recognized the symmetry of the even function. You might say, what are you talking about? Well, instead of integrating from -2 to 2, I'm going to integrate from 0 to 2. And kids will go, you can't do that. Mr. Dobner, look at this. You're saying you're just doing that. Well, I'm not done yet. What do you think I'm going to do? Multiply by 2. That's what an even function allows you to do. And some kids will say, I just saw it with the symmetry. Yeah, cool. That's great. Kids will say it's the same area in what I've had in green as what you'd have in yellow by the symmetry of the curve there. Yeah, that's what an even function's all about. Now, why would you do this? I don't know about you. I think it's way easier to plug in a 0 as a lower bound than a -2. Do you have to do that? No. And kids will say, what if I just worked it out, without doing that whatsoever? Oh, you'll get the right answer. You certainly will. Talking about the right answer, let's just think about this for a second, just finishing it. I'm going to pull a 2 pi out, and I can't do a u substitution. You could try, but wow, I want to point this out to you. This is so important. There is a property of squaring. You really should know this. What is a minus b squared? a squared minus 2ab plus b squared. And you'd say, why are you doing that? Well, here's your a, here's your b. A squared is 16 minus 2 times a times b. And then you'd say, plus your b squared. Well, that's x to the 4th. And you'd say, well, why'd you do that? Well, now I can work this problem out. Now it's not so bad at all. Maybe it's not the simplest problem to work out. Forgive me, I wrote a 5 there. I'm getting ahead of myself. Excuse me, my eraser here didn't kick in. There we go. But you can see where we're going with this. I can expand it so that I can now do an antiderivative, right? So let's real quickly just finish this up. It's not letting me move over a little bit. There we go. So I'm going to take my 2 pi antiderivative of all this. What do we get, guys? What's the antiderivative of 16? That's the derivative. That's the derivative of 16. 16x. How about this one? We'd have minus 8 thirds x to the 3rd. Ooh, what's the antiderivative of x to the 4th? X to the 5th over 5. And now you can see why it's nicer to not have that negative 2. Right? Now you're just saying, well, I've got my 2 pi here. And plugging in a 2 for each of these, it's still, 16 times 2 minus 8 thirds times a 2 to the 3rd plus 2 to the 5th all over a 5. And then you'd say, well, plugging in a 0, that's just going to get you a 0 everywhere. So 16 times 2 is 32. This is 8. 8 times 8 is 64. 2 to the 5th is 32. That's 32 over 5. And now it's just number crunching. Now it's just number crunching, right? And you could say, well, hey, could we real quickly get a common denominator? Yeah, maybe a 15. 15 right there. Tell you what. So this would be what? 480 over 15. Right? This is what? 320 over 15. And this is 96 over 15. And then you just have to finish this all up. 480 minus 320. Well, I think we know what's happening there. That's 160. Then you add 96 to it. And you're at 256. So here's 256 all over 15. And when you double 256, you'll get what? 512, I guess. So this would be the exact volume that we have.